distance. It feels so solid, right?
Yeah, really concrete, tied to the world we see.
Tied to the world we can see and touch. But what if you could apply that same idea, measurement, understanding, shape, to spaces with infinite dimensions? What would that even look like? Why would you need it?
It's a concept that seems to defy our everyday intuition of space, definitely. How do you measure distance or angle when you can't even, well, picture the space?
Exactly. And that's the core idea we're digging into today. We're going deep into this concept called Hilbert spaces. They take those familiar geometric rules we know from 2D or 3D space and powerfully extend them to spaces of any dimension, including infinite ones.
And the big insight here.
Well, it's not just some mathematical curiosity. It turns out it's the fundamental language used to describe everything from, the strangeness of quantum particles to the signals powering your phone.
Right. It's where pure mathematical abstraction really meets the bedrock of physics and engineering. It's quite something.
We're pulling insights today from some material. A listener shared excerpts from a detailed analysis called Understanding Hilbert Spaces, Theory and Applications.
Okay.
So our mission for this deep dive is to figure out what a Hilbert space actually is, understand the key ideas that build it up, and then explore why this abstract idea is surprisingly essential to modern science and technology.
Sounds like a good plan. So let's unpack it.
So where did this whole journey into infinite dimensional geometry even begin? It feels like such a leap from, triangles and squares.
It really does. The concept started taking shape in the early 20th century, largely driven by the German mathematician David Hilbert.
Hilbert, okay.
But interestingly, he wasn't setting out to invent infinite dimensional geometry explicitly.
Yeah.
He was focused on problems involving integral equations.
Integral equations, so more analysis, not geometry at first.
Precisely.
Yeah.
His work was a significant departure from the more traditional, visually concrete geometry of earlier eras. But his investigations into these equations laid critical groundwork for a whole new field called functional analysis.
Functional analysis,
Yep.
right? The study of spaces of functions, using ideas from algebra and analysis like limits.
Yes, exactly. Spaces where the vectors can be functions or sequences, and you have structures that let you talk about limits and convergence. Hilbert's work provided some of the very first really crucial examples of these kinds of spaces.
And they were immediately called Hilbert spaces. Did he name them after himself?
No, actually. That name came later. It was introduced in the 1920s by the brilliant mathematician and physicist John von Neumann.
Von Neumann,
Yeah.
of course. Computing, quantum mechanics, a giant. Why did he put Hilbert's name on these spaces?
Well, von Neumann was deeply involved in setting up the rigorous mathematical structure of quantum mechanics. He recognized that these abstract spaces emerging from Hilbert's work, these complete inner product spaces, were the perfect mathematical language, just what was needed to describe the states and observables of quantum systems.
Wow, that's a remarkable jump. A mathematical idea developed from integral equations finds its absolutely necessary home in describing the subatomic world decades later.
Amazing. It really speaks to the interconnectedness of mathematical thought, doesn't it? And it wasn't solely Hilbert and von Neumann. Mathematicians like Frigyes, Riesz, and Erhard Schmidt also made really foundational contributions to the theory.
So roots in integral equations, growing up in functional analysis, and the name really solidified because it was essential for quantum mechanics. That's a fascinating lineage.
Definitely.
All right, with that historical context, let's build up the concept itself. You mentioned they generalized Euclidean space. So how do we actually construct one of these Hilbert spaces? What are the essential ingredients?
Okay. Think of it like assembling a mathematical object with specific properties. The first layer is the basic structure you're probably familiar with from linear algebra, a vector space.
Okay, right. A collection of things we call vectors, could be arrows, could be functions, could be sequences that we can add together and multiply by numbers, scalars, following the usual rules.
Exactly. It gives us the basic framework for linear combinations, adding and scaling. But for geometry, we need more. The next really crucial ingredient is what turns a simple vector space into an inner product space.
And that's where the idea of measurement comes in, right? Lengths, angles.
Yes. An inner product is an operation. It takes two vectors and gives you back a single number, a scalar. It's the direct generalization of the dot product you use in regular 2D or 3D space.
The one we use to find projections or calculate magnitudes.
That's the one. It captures that idea of overlap or, how much two vectors are aligned, essentially.
Okay.
The source highlights the specific properties this operation must satisfy, things like conjugate symmetry, linearity, positive definiteness. But the key takeaway is that these rules ensure the inner product behaves consistently. And that allows us to define fundamental geometric concepts.
Like length and angle.
Yes. With an inner product, we can define the norm or length of a vector. It's just the square root of the inner product of the vector with itself. And crucially, just like with the dot product, the inner product lets us define the angle between two vectors. This is what gives the space its geometric structure.
Got it. So a vector space gives us linear combinations. An inner product space adds the geometry measuring length and angle. What's the final piece then? What makes it a Hilbert space?
That's the property of completeness. It's an analytic property.
Completeness.
Okay, so an inner product space, because it has a norm and thus a distance function, xy, is also something called a metric space. Now consider a sequence of vectors in this space. A Cauchy sequence is one where the vectors get arbitrarily close to each other as you go further out in the sequence. They look like they're heading towards some specific point.
Like points closing in on a target, getting closer and closer together.
Right. A space is complete if every single Cauchy sequence in the space actually converges, and this is the key part. Its limit is also a point that exists within that same space. There are no missing points, no holes, where a sequence might seem to converge, but the target isn't actually in the space.
Can you give us an example of a space that isn't complete? I think the source mentioned one that's really helpful.
It does, yeah, and it's a great way to see this idea. Consider the rational numbers you can write as a fraction, like 12 or 34.
Okay.
Now think about the sequence you get by writing out the decimal expansion of pi. 3, then 3.1, 3.14, 3.141, 3.1415, and so on.
Right, adding more digits each time.
Each number in that sequence is rational. You can write 3.14 as 314,100. And as you go along, the numbers get closer and closer to each other. They definitely form a Cauchy sequence within the space of rational numbers.
That sequence converges to pi.
Exactly, and pi is irrational. You can't write it as a fraction. So you have a sequence in the space of rationals that looks like it's converging, but its limit, pi, is outside the space. The rationals have holes where the irrational numbers should be.
Okay. But the real numbers don't have those holes.
Correct. The real numbers are complete. Any Cauchy sequence of real numbers converges to another real number. There are no gaps.
That makes total sense. So a Hilbert space is this special kind of space that brings it all together. It's a vector space, it has an inner product for geometry, and it's complete, so it has no holes.
Precisely. And here's the powerful insight. It's the combination of that algebraic structure, the geometric measurement from the inner product, and this analytic rigor of completeness that makes Hilbert spaces such robust and versatile tools.
Especially when dealing with infinite dimensions or continuous processes.
Exactly. Which is essential for areas like quantum mechanics or signal analysis. It handles the complexities.
Okay, so we have the definition. Vector space plus inner product plus completeness. Now, what are some of the fundamental ideas or theorems that, live inside these spaces? What can you do with them?
Well, there are several that are absolutely key. One you've probably encountered in some form before is the Cauchy-Schwarz inequality.
Right, I remember that. It relates the dot product to the lengths of vectors in normal space.
It's the generalization of exactly that. For any two vectors, x and y, in a Hilbert space, the magnitude of their inner product, written xy, is always less than or equal to the product of their individual lengths or norms, x times y.
So x, y, x, y, it feels like it's saying the overlap, the inner product, can't be bigger than the vector's own sizes would allow. Is that a fair way to think about it?
That's a very good way to think about it.
Yeah.
And equality only holds if the vectors are essentially pointing in the same or opposite directions. They're linearly dependent.
And why is it so important?
Its importance, as the source notes, is that it's a fundamental workhorse inequality. It gets used in countless proofs within Hilbert spaces and functional analysis, including, for example, proving the triangle inequality for the norm, which basically says x plus y, the path length idea.
Okay, a core inequality. Makes sense. What about representing vectors? In 3D, we love using the x, y, z axes, their perpendicular unit length.
Ah, yes. That brings us to orthonormality, a concept that feels incredibly intuitive thanks to our experience with Euclidean space. So two vectors are orthogonal if their inner product is 0. They are perpendicular in this generalized sense.
Got it. Inner product 0 means orthogonal.
And an orthonormal set is a collection of vectors where they are all mutually orthogonal to each other, and each one has a norm or length of exactly 1.
So a set of perpendicular unit vectors, basically.
Exactly, like your x, y, z axes. And an orthonormal basis is such a set that spans the entire space, meaning any vector in the space can be uniquely represented as a linear combination of some of these basis vectors.
Wow. So it's like having those perfect perpendicular unit-length axes available even in infinite dimensions.
Precisely. The source mentions that if a Hilbert space has a countable orthonormal basis, it's called separable. That's an important technical property, especially in applications. But the core idea is having this perfect coordinate system.
Having an orthonormal basis seems incredibly powerful. You could break down complex vectors or maybe even functions into simpler components using it.
It's absolutely fundamental for that. Okay, what's another big result?
Yeah, what else?
The Riesz representation theorem. This one is maybe a bit more abstract, but it connects certain types of maps on the space back to vectors within the space.
Okay. What kind of maps are we talking about?
Specifically, continuous linear functionals. So these are linear maps. They respect addition and scalar multiplication that take a vector from the Hilbert space and produce a scalar, just a number.
So a linear function that eats a vector from the space and spits out a number.
Right. The Riesz representation theorem states something quite remarkable. For every single one of these continuous linear functionals, let's call it f, there is a unique vector y living in that same Hilbert space, such that applying the functional f to any vector x gives the exact same result as simply taking the inner product of x with that special vector y.
So fx is the same as xy
Right.
for some specific y?
Exactly. fx, x, y. For every continuous linear functional f, there's a unique y that does the job.
That's quite something. It means every continuous way of linearly turning a vector into a number can be boiled down to just taking its inner product with one specific vector from the space itself. It gives a concrete representation for these abstract functional things.
It really does. It highlights a deep duality between the space and its space of functionals and provides a powerful tool for analysis within Hilbert spaces.
Okay, fascinating stuff. We've built the structure, looked at some fundamental properties like Cauchy-Schwarz and Riesz. Let's try and make this less abstract again. What are some real important examples of Hilbert spaces?
Well, the most straightforward examples are the finite dimensional ones we started with, Euclidean spaces.
Like the familiar 2D plane, R, or a 3D space, R using the standard dot product.
Yes, exactly. R, real n-dimensional space, and
Yeah.
C, complex n-dimensional space, with the standard dot product serving as the inner product. They tick all the boxes, vector space, inner product, and they are complete. These are the simplest cases, with our geometric intuition works pretty directly.
But where it gets really mind-bending, I guess, is the infinite dimensional ones.
Yeah.
You mentioned functions and sequences could be vectors.
Exactly. This is where the vectors stop being simple lists of numbers. A really critical example, mentioned in the source, is the space of square integrable functions, often denoted as L spaces, L2.
Functions as vectors.
Yeah.
Okay, tell me more about L.
So in these spaces, the vectors are functions, maybe defined on an interval like AB. The condition that makes them part of the space is that the integral of the square of their magnitude over that interval must be finite. Fx dx has to be less than infinity.
Y square integrable. Why the square?
That condition ensures that the size or length of the function, which is defined by the norm that comes from the inner product, is actually a finite number.
Okay, and the inner product itself. How do you do a dot product with functions?
It's defined using an integral. The inner product between two functions, f and g, in this space is f, g of x times dx dx, where g is the complex conjugate of g. You integrate the product over the interval.
Right, the complex conjugate for generality.
Yes, and this definition satisfies all the rules for an inner product. So it allows us to define geometric relationships between functions. We can talk about functions being orthogonal, for instance.
So we can talk about the angle or distance between two functions. That's stretching my mind a bit.
It certainly stretches traditional thinking. It's incredibly powerful, though. Another key infinite dimensional example involves sequence spaces, like L. Little L2 this time.
Okay, LL, what are the vectors here?
Here, the vectors are infinite sequences of numbers, usually complex numbers. X, X, X. It's just going on forever.
An endless list.
An endless list. The defining condition here, similar to LO, is that the sum of the squares of the magnitudes of the terms must be finite. LSNS, there's a finite sense. Again, this ensures the sequence vector has a finite length in this space.
And the inner product for these infinite sequences, still like a dot product.
It is, essentially. It's defined by an infinite sum. The inner product of sequence, xn, and sequence yn is O, x, and u1. So you multiply corresponding terms with conjugation and sum them all up. assuming the sum converges, which it will for sequences in L.
Okay. So whether it's finite lists of numbers like in R, or functions whose squares are integrable like in L, or infinite sequences whose squared terms sum up like in LR, if they fit the vector space, inner product, and completeness criteria, they are Hilbert spaces.
That's right.
And we can apply all this powerful geometric and analytical machinery to them, regardless of what the vectors actually are.
Exactly. They provide this amazingly unified mathematical language for dealing with incredibly diverse mathematical objects.
Right, we've built up the concept from its foundations, seen some key properties, looked at examples. Now for the part that connects it all back to the listener. Why should someone who isn't a mathematician care about these abstract spaces? So what does this all mean for the real world?
Ah, yes. This is where the power becomes really apparent. Hilbert spaces are not just theoretical constructs. They are absolutely fundamental to describing the physical world and enabling modern technology. The most profound application, arguably, is in quantum mechanics.
The physics of the very small electrons, photons, atoms, I know that gets weird, probabilistic, uncertain.
Yes, it is inherently weird, yeah. And Hilbert spaces provide the essential mathematical language to describe it rigorously. In quantum mechanics, the possible states of a quantum system, like an electron, aren't just points in regular space. They are represented by vectors in a complex Hilbert space, often an infinite dimensional one, like Erhard.
A vector in an abstract space represents the physical state of a particle. Okay.
Exactly. And the things you can measure about that system observables, like position, momentum, energy, spin, are represented by specific kinds of linear operators called self-adjoint operators, acting on these state vectors.
Operators acting on the state vectors and the results of measurements.
The possible outcomes you might get from a measurement correspond to the eigenvalues of these operators.
Eigenvalues. Okay.
Yeah.
And probabilities.
Like,
Quantum mechanics is all about probabilities, isn't it?
Yeah.
Where they come in.
It is, and the probability of getting a particular measurement outcome is directly related to the inner product. Specifically, it involves the square of the magnitude of the inner product of the state vector with the corresponding eigenvector of the operator. Hilbert spaces give us the structure to define states, measurements, and probabilities in a consistent, powerful way for the quantum realm.
That's incredible. So we're taking this abstract mathematical structure, vector spaces, inner products, completeness, and using it as the literal language for reality at its most fundamental probabilistic level.
It's really one of the great triumphs of 20th century mathematical physics. It works astonishingly well.
Wow. Okay, what else? Any other big applications?
Another major area is Fourier analysis.
Right, which is all about breaking down signals or functions into simpler ways, sines and cosines.
Precisely. Fourier analysis decomposes a complex function or signal into a sum, potentially an infinite sum, of simpler oscillating components. And Hilbert spaces, particularly the L space of square integrable functions, provide the perfect setting for this.
How so?
Because, as the source mentions, a specific set of these oscillating functions, like complex exponentials, e-to-things, actually forms an orthonormal basis in the Hilbert space L while defined on an interval like 0, 1.
Ah, like our generalized axes idea from earlier.
Yeah.
So expressing a function as a Fourier series is just representing that function vector in terms of this specific orthonormal basis in the L Hilbert space.
You've got it exactly. It's using the geometric concept of an orthonormal basis to understand the composition of functions or signals. And this is absolutely key to understanding waves, vibrations, acoustics, image processing, many kinds of signals.
And that leads directly into signal processing, I imagine.
Yes, absolutely. In fields like audio engineering, telecommunications, radar, even medical imaging like MRI, signals, whether they're sound waves, radio waves, data streams, are routinely treated as vectors in Hilbert spaces.
Why is that the go-to approach? What does it buy the engineers?
Because it allows them to bring the entire powerful toolbox of linear algebra and geometric intuition from Hilbert spaces to bear on analyzing and manipulating these signals.
Can you give an example?
Sure. Think about noise reduction. The concept of orthogonality perpendicularity is used directly. You can try to design filters that project the received signal onto a subspace that represents the clean signal, effectively removing noise components that are orthogonal to it in the Hilbert space sense.
That's a wonderfully concrete example of using orthogonality in practice, separating signal from noise.
Exactly. And the Fourier transform itself, which is absolutely foundational to signal processing for analyzing frequency content, is most elegantly and powerfully understood within the Hilbert space framework, particularly Elucia.
So this isn't just theoretical physics. This math is directly enabling the technology we use every single day, our phones, Wi-Fi, music streaming, medical scans.
It's woven deeply into the fabric of modern engineered systems. It's often hidden, but it's there.
This has been a truly fascinating deep dive. We've gone from the abstract definition of these spaces, vector space, inner product, completeness, through key ideas like orthogonality and Riesz, to their indispensable role in describing the quantum universe and building our technology.
Hilbert spaces really are a beautiful testament, as the source says, to the unifying power of abstract mathematical ideas. They successfully extend that intuitive geometry of Euclidean space into infinite dimensions, and in doing so provide the essential tools for quantum mechanics, analysis, and signal processing.
It's quite amazing to think that a concept stemming from what integral equations about a century ago could become the language of the quantum world and the engine behind our connected devices.
They are truly indispensable tools in modern science and engineering, there's no question.
So here's something to think about, maybe a final thought for you listening. Given that these abstract mathematical structures, like Hilbert spaces, turned out to be the very bedrock for describing physical reality at its most fundamental level and for practical technologies, well, what other seemingly abstract mathematical concepts, maybe ones being studied today with no immediate application in mind, might hold the key to understanding or building the world around us in ways we can't yet even imagine?
It definitely underscores the often hidden long-term value and potential hiding within abstract thought and pure mathematics.
Something to ponder indeed. We hope this deep dive has given you a new perspective on the power and, maybe, the surprising relevance of abstract mathematics in our world.